Hello everybody, today we are going to discuss fluid solid non-catalytic reactions and reactors, and in this module we will follow the textbook by Octave Levenspiel. The module outline, the first one we will discuss the fluid solid non-catalytic reactions, and then we will discuss fluid solid non-catalytic reactor design. We will start with fluid solid non-catalytic reactions. These reactions are extremely important and very widely experienced and seen in different type of industries, chemical industries, metallurgical industries. Let us take an example, say 1 mole of A, which is the fluid reactant, reacts with B moles of B, which is a solid reactant, to produce fluid products and solid products. The different examples of such reactions are pyrolysis of coal and biomass, the combustion and gasification of coal, calcination of limestone, roasting of ores, smelting of metal oxides. Different models have been proposed to describe these reactions. The one such model is progressive conversion model. These progressive conversion models are very highly suitable for porous particles. The fluid reactant basically diffuses to the surface of the solid particle, then diffuses into the solid particle and reacts with the solid particle. The reaction takes place throughout the volume of the solid particle, but due to the mass transfer resistance, the rate of the concentration of the fluid concentration of the fluid A reactant decreases from the surface to the center, and as a result the rate of reaction also decreases from the surface to the center. The solid concentration on the other hand increases from the surface to the center, because more reaction takes place near the surface. Another popular model which is more widely used, that is shrinking core model, which was proposed by Yagi and Cooney. This is more applicable for non-porous particles, unlike the previous one which was more applicable for the porous particles. In this model, it is assumed that the reaction takes place at a sharp interface. It starts at the surface of the particle, and then gradually the product layer thickness increases. The reaction takes place at the sharp interface between the product layer and the unreacted core, which is shrinking. The concentration of the solid reactant is step type, 0 in the product layer and 0 in the shrinking core, 0 in the product layer, and it retains its original concentration throughout the core. Gradually the volume of the core decreases, and finally it reduces to a point where the conversion is completed. So, the reaction interface recedes inward with time topochemically. An irreversible reaction, we will consider this shrinking core model for an irreversible reaction, and an irreversible reaction is assumed to take place in 3 steps, overcoming 3 individual resistances in series. You can see that the particle is surrounded by the gaseous fluid reactant. The fluid reactant diffuses across a stagnant film around the solid particle, reaches the surface, and then it diffuses through the product layer, reaches the reaction interface, and then it reacts. So, the first step is it has to overcome the diffusion resistance in the surrounding stagnant gas film. Then the second resistance is step 2, it has to overcome the diffusion resistance in the product layer, and the third resistance is the chemical reaction resistance at the reaction interface. But all these resistances may not be significant all the time. Sometimes one of these resistances may be dominant and rate controlling. We will we will present the conversion versus time relationship using the shrinking core model, and for different cases we will assume that the reaction is controlled by one resistance at a time. We will make certain assumptions. Of course, the first assumption is zero diffusivity in the shrinking core. The second one is that the heat transfer resistance is neglected. The third one is the particle size remains constant, then single reaction, irreversible reaction, first order reaction, and non-equimolar counter diffusion is not considered, and we will assume pseudo steady state. First we take up case 1, that is it is controlled, the reaction is controlled by the diffusion through the stagnant gas film around the particle. Now, here we assume that the resistance, the other two resistances, that is the product layer diffusion resistance and the chemical reaction resistance is negligible. The rate of reaction at for the particle is assumed to be equal to the rate of diffusion at the particle surface, and we derive this relationship between R c and T, where R c is the radius of the shrinking core at any point of time. So, equation 2 gives us the relationship between R c and T, and when R c becomes 0, the reaction is complete, T becomes tau, tau is the reaction completion time, and equation 3 gives us the expression for tau. And then the conversion of the solid reactant is defined as say 1 minus x p is the volume of the unreacted core to the volume of the total volume of the particle. And so, the relationship between the conversion and R c is given by equation 5, which is 1 minus x p is equal to R c by R, capital R, that is the particle radius whole cube. And using combining these equations, we arrive at the conversion versus time relationship for this case 1, that is diffusion through gas film control, which is T by tau is equal to x p, that is conversion is proportional to the reaction time. Then we take up the second case, that is the reaction is controlled by the product layer diffusion. Here we are ignoring the other two resistances. So, the entire drop in concentration of the gas takes place over the product layer. So, we see that the concentration of the gas drops from CAG to 0 at the interface. Now, for gas solid reactions, the shrinking of core or the movement of the reaction interface, that is very slow, much slower than the velocity of diffusion of the fluid reactant towards the reactant interface by a factor of about maybe more than 10 to the power 3. So, the reaction interface may be assumed to be stationary when we want to calculate the concentration gradient of A. So, this assumption is called pseudo steady state assumption, and we will use this assumption in this derivation. But mind it, we can use this assumption only for gas solid reactions, not for solid liquid reactions, because for solid liquid reactions the factor is in the order of 1. So, the rate of reaction at the reaction interface is assumed to be equal to the rate of diffusion of A to the interface. So, we derive the equation 7 which correlates R c versus T, and tau by equation 8 we find that tau is proportional to R square. And then finally, we also derive the conversion versus time relationship. Here we find that it bears a nonlinear relationship between x p and t reaction time. Now, we go to the case 3, where it is entirely dominated by the chemical reaction resistance. So, we see that the other two resistance being negligible, the entire concentration drop takes place sharply at the reaction interface. So, from CAG to 0, it drops at the reaction interface, and the RC versus T relationship is presented in equation 11, and the tau is expressed in equation 12, and we find that tau is proportional to the particle radius r in this case, and the equation 13 gives us a relationship between the conversion and reaction time, which is again nonlinear, and 1 minus x p is equal to 1 minus t by tau whole cube. Now, if we considered, because so far we have considered 3 individual cases predominating controlling the reaction, if all the 3 resistances are considered simultaneously, then tau, that is the reaction completion time, will be summation of the 3 individual reaction completion time. So, tau is equal to tau 1 plus tau 2 plus tau 3. So, we put those values of tau 1, tau 2 and tau 3 for the 3 different controlling resistances, and equation 14 gives us the expression for tau. And also combining the results of the 3 individual resistance controls, we get the conversion versus time relationship for a case where all 3 resistances should be considered. In some reactions, the solid product is not formed, only fluid product is formed. So, in that case, the solid product layer is absent, and the solid reactant getting consumed, the radius of the solid particle also changes with time, it reduces with time. So, in this case, there are 2 resistances only, not 3 as in shrinking core model. One is of course gas film diffusion control, gas film diffusion resistance. The second one is the chemical reaction resistance. We take up the first case, that is gas film diffusion resistance control. Now, the derivation is absolutely similar to what we did in shrinking core model, but in that case kg, because kg is a function of r, in that case r was constant. So, kg was constant, but now the particle radius r is varying, it is reducing. As a result, kg will also change. So, this variation we will get from Frostling equation, and we find that Frostling equation has got 2 terms. If the Reynolds number value is small, the contribution of the second term is very small, can be neglected, and in that case kg will be inversely proportional to the diameter or inversely proportional to the radius. When the Reynolds number is high, that is for large particle size or maybe high velocity, then the contribution of the first term is negligible, and then the kg mass transfer coefficient is proportional to 1 by square root of dp. So, or 1 by square root of r. So, we will use these relationships equation 17 and 18 while deriving the conversion versus time relationship. For small, first we take up small particles, Stokes regime, the radius versus time relationship, because here radius is a function of time. Radius versus time relationship is given by equation 19, and the reaction completion time is shown in equation 20, and it is seen that reaction completion time is proportional to the initial particle radius square, and equation 21 gives us the relationship between the conversion and time. For large particles, the the relationship between Kg and R is different. Using that, tau is we find that it is proportional to R0 to the power 1.5, and equation 23 gives us the relationship between conversion and time. If it is controlled by chemical reaction resistance, the same equations that we derived for shrinking core model may be used here also. So, that is the equation 24 which we derived in the previous shrinking core model 2. Now, we have derived different conversion versus time relationship for using shrinking core model, assuming one of the resistance to be rate controlling. But how do we know which resistance is rate controlling for the reaction? For that we need to carry out some experiments, and the experimental results need to be analyzed. First, we know that we have already derived the conversion versus time relationship, and we have seen that a function of x p, that is a conversion, is equal to t by tau for all three cases. But this function is different. You see, we show this function of x b. This is for gas film diffusion control, this is for product layer diffusion control, and this is for chemical reaction resistance control. Now, what we do is, if the experimental results, we will get conversion and the time of at different time of reaction, and we will plot this f of x p versus t, and we will check for the linearity, and the one which shows the best linearity indicates the rate controlling resistance. But quite often the experimental results may be somewhat scattered, sometimes some errors are there. So, just one check is not good enough always. So, then we can also check with the experimental results of different particles size, and we know that to achieve we have already derived these equations, to achieve the same conversion, the time required will be proportional to r raised to the power some exponent, and this exponent is different for different controlling resistance. This exponent will be 1 for chemical reaction control, 2 for product layer diffusion control, and varying from 1.5 to 2 for gas film diffusion control. So, we plot log of this t for a fixed x p, could be 50%, could be 75% conversion, we will fix it up that first, versus log of r, that is the particle radius that you have taken, and we will carry out these experiments for different particle radius, and we will plot this log of t x p versus log of r and find out the slope. If the slope is 1, chemical reaction control; if the slope is 2, it is product layer diffusion control, and if the slope varies from 1.5 to 2, it is gas film diffusion control. Then we can also study the effect of temperature on the reaction rate. That will also give an idea about the rate controlling resistance. If temperature has a very high influence on the reaction rate, then chemical reaction may be rate controlling. If the effect is very marginal, nominal, then product layer diffusion control is possible, and if it is somewhat intermediate, moderate, maybe gas film diffusion control. Normally, it is seen that at low temperatures chemical reaction becomes dominant and rate controlling. At high temperature, of course, the mass transfer resistances become dominant. If the change in velocity affects the gas film, affects the experimental results, reaction behavior, then it is gas film diffusion control, particularly with large particles. If the product formed is a hard and non-flaking type with low porosity, then usually product layer diffusion resistance is rate controlling. But shrinking core model, though it is very popular and widely used, it has got certain limitations. It is not well suited for highly porous particles. The reaction interface, it is assumed to be sharp, need not be necessarily always very sharp, maybe diffused, and also it does not incorporate the structural details. So, some structural models have also been proposed, grain model, where particle pellet is assumed to be constituted of a large number of small grains, and each grain is assumed to follow the shrinking core model. Another model proposed was random pore model. In this model, the pore structure evolution with conversion is incorporated. So, we have had a fairly detailed discussion on fluid solid non-catalytic reactions, single particle. Now, we will incorporate this knowledge into the fluid solid non-catalytic reactors and its design. The design of fluid solid non-catalytic reactors, there are three controlling factors. The first controlling factor is of course, the reaction behavior of the single particle, which we have already discussed. The second factor is the size distribution of the solid particles, and the third factor is the flow patterns or the contacting patterns of the solid as well as the gaseous reactants. Different type of contacting is possible. Say solid and gas both may be in plug flow, like in blast furnace or rotary kiln. Number 2, the solid may be in mixed flow, like in fluidized bed reactors. Third, maybe batch process. Fourth, maybe semi batch process, maybe the solid is in fixed bed and the gas is in plug flow, like in ion exchange column. In the design of fluid solid non-catalytic reactors, we will make one basic assumption, and that is the gas composition remains uniform throughout the reactor, and this assumption is reasonably valid if the conversion with respect to the gas or fluid is small, or if the fluid back mixing is large. Now, we will take up three cases. The first case is the particle is of single size and the solid is in plug flow. Now, we know that if the solid is in plug flow, all the solid particles will stay in the reactor for the same period of time, same residence time, and all the solid particles have got the same radius. So, each particle will be converted to the same extent. So, that means the mean conversion of all the particles which are leaving the reactor will be equal to the conversion of each individual particle. So, we go back to the single particle reaction behavior, we have derived the equations and we calculate the mean conversion using the single particle reaction behavior, and that will be our mean conversion for the reactor. The second case, the particles are still in plug flow, but the particles are of different size, constant size, unchanging size, but there is a wide size fraction range. So, here we will denote this total volumetric flow rate of the solid particles as F, and F of Ri is the volumetric feed rate of the solid particles which have a radius of particle radius of Ri, and Rm is the largest particle radius of the solid particles. So, that means the size varies from 0 to Rm. So, of course, the F is equal to the summation of F of Ri from Ri varying from 0 to Rm. Now, as the solid is in plug flow, all particles stay in the reactor for the same period of time T p. Now, we want to find out the mean conversion of the particles. Different particles will have different conversion because they are of different size. So, we derive that using this approach. We take up the particles of a particular size fraction, say R I, and we find out the fraction of B, that is a solid reactant, unconverted in the particles having a radius of R in this size range, size fraction, and this is multiplied with the fraction of the feed which has a particle radius of R I. So, this product of this term and this term gives us the contribution of the particles of this size R I, size fraction R I, to the fraction of the unconverted B overall. So, if you want to find out the mean value of the unconverted B in the exit stream, we will sum it up for the all the particles having different size ranges. So, this is the equation that we will use. So, equation 26 is 1 minus x b bar is the mean conversion of the solid, and 1 minus x b bar is the mean unconverted B fraction, that is the summation of these two, the product of these two terms, 1 minus x b, which is a function of R I, and the fraction is given by f of R I by f. Now, interestingly, we can see that the lower limit has been changed from 0 to R at T p is equal to tau. Why so? Because R at T p is equal to tau is the radius of the largest particle that will be completely converted in the reactor. The particles which have got smaller radius will be fully reacted in the reactor and will have no contribution to the mean unconverted B. So, naturally the lower limit has been changed. Now, this 1 minus x b is a function of R I. So, this we will express in terms of T by tau, and reaction time T is here is T p, because all the particles have got the residence time of T p. So, we replace this 1 minus x b. If it is gas film diffusion control, we know that x b is T by tau. So, we replace it 1 minus x b, we replace it by 1 minus T p by tau, which is a function of R I, and we sum it up and we get the mean conversion of B, and 1 minus x b bar is the mean unconverted. And if it is controlled by the chemical reaction, then this 1 minus x p is replaced by 1 minus, we know that 1 minus x b is 1 minus T by tau whole cube, and here it is T is replaced by T p. So, it is 1 minus T p by tau whole cube, and it is summed up for all the particle sizes. Then we take up the case 3, where we use a mixed flow of solid, but the solid particle sizes are same, constant and same. So, here because the solid particles are in mixed flow, we know that in mixed flow the residence time will be varying widely from 0 to infinity over a wide range. So, here we divide the entire residence time range into small time intervals, and we take one small residence time interval and we find out the fraction of B unconverted for such particles which have got a residence time between t and t plus dt. And then this fraction is multiplied with the fraction of such particles, that is having residence time between t and t plus dt, and this product gives us the contribution of such particles to the mean value of the B unconverted. So, we write this equation 29, that is 1 minus x b bar is integral of this 1 minus x b, and we know this fraction is nothing but residence time distribution function multiplied by dt, and we write that 0 to infinity. And but here we see that the upper limit has been changed from infinity to tau. Why? Because if the residence time exceeds reaction completion time, it is already completed, completely reacted, and it will have not have any contribution to the mean unconverted. So, E of t we already know that for ideal mixed flow cases, E of t is given by e to the power minus t by t bar divided by t bar, where t bar is the mean residence time. So, we replace the second term here by E of t by this. It may be gas film resistance control, and there we know that this 1 minus t by tau, this it is 1 minus t by tau is equal to 1 minus x p. So, we replace 1 minus x p by 1 minus t by tau, and using integration by parts we get the expression for mean conversion of B x b bar. If it is chemical reaction controlled, we know that 1 minus x b is 1 minus t by tau whole cube. So, this 1 minus x b is replaced by this, and using integration by parts and recursion formula we derived equation 32 for x b bar. And if it is product layer diffusion control, then again the 1 minus x b bar is expressed by equation 33. And when we find the holding time required to achieve the same conversion for mixed flow to the plug flow, we find this ratio is always greater than 1, and this ratio increases with conversion. So, in this module we have first discussed about the fluid solid non-catalytic reactions. We have primarily discussed gas solid non-catalytic reactions. Different models we have discussed. We have used the shrinking core model in detail, 3 resistances in series for irreversible reactions, and then we have also learnt how to identify the rate controlling resistances. And finally, we have also discussed the fluid solid non-catalytic reactor design. We have learned that 3 factors predominantly control such design, and we have considered 3 cases. One is particles of single size, solid is in plug flow, and then second one particles of different but unchanging size, solid is in plug flow, and third one is particles are in mixed flow, but having single unchanging size. Thank you.